Is non-destructive load testing of bridges, an Oregon perspective. Our presenter, Travis Kinney. Travis has been the major bridge maintenance engineer for ODOT for 7 years. Please welcome Travis.
Extending the life of bridges, expanding it beyond just keeping the condition of the bridge good, but keeping that bridge in service is a subject that's been kind of a passion of mine. It would drive me nuts as I'm doing maintenance and rehab and keeping some of these bridges that are in poor condition, up and in service when they go through and knock down a bridge that's in great condition because of one of the serviceability aspects, and kind of going like, come on, that's not the bridge we need to replace. We need to replace the ones that are in awful condition so that we can preserve the ones that are worth preserving. Keeping good bridges in service. So ODOT's been using live load testing since about the 90s with this goal. It's that going after something on paper says this bridge needs to be posted, restricted, or replaced. When you go out and look at it and say, wow, that bridge is in really good condition, something that Matt alluded to. It's a hard kind of gap to bridge. That is exactly where load testing comes in as a useful means. You get at closing that gap between what engineers do with their conservative assumption base, right? Engineers are just big estimators. We have a lot of math and theory that goes behind it, but when it's said and done, we like to present our answers as this is the answer, and that is simply not the case. Right? It's all based on your assumptions that went into that analysis. And load testing lets you actually get out and measure how that structure responds. It's a huge value to an owner. Let's kind of run through 2 case studies. We might be more like 1.5. We'll see where we get. Okay, so load testing, it is covered in the Manual for Bridge Evaluation. Section 8 gives you a lot of guidance on how to use it. That is what ODOT has used historically. There's really 2 different types of testing. There's diagnostic and proof testing. And I'll run through why you'd want to use one versus the other. Proof load testing. This is typically only considered when you have these categories. You don't really know the bridge details. Well, you have to be very careful as you're doing this. You don't want to have a sudden failure during your test. A diagnostic load test can't be utilized. And I'll get into why diagnostic is option A and proof test is option B. And then also from an ODOT perspective, we usually look at these as being, if you're happy with just legal loads, not all those special hauling vehicles, not the Franken emergency vehicles that we're now designing for and rating for. But if you're okay with the 3 typical legal vehicles, then proof testing could be a good option for you. Much above that, you're gonna have to either extrapolate or really put a lot of load on the bridge. And that is one thing that I do like to highlight is during a proof test, we will typically intentionally actually place more load on that bridge than it may have seen in its entire life. So something to think about before you set out to do it. Diagnostic load testing. So this is where you're really trying to refine your analysis. You're getting better at your assumptions by getting good measurements of the structure. In this case, you've already been able to do an analytical load rating. It just doesn't convey how the structure is actually performing. There aren't really signs of significant live load distress. You could kind of squabble over what does significant mean. To me, the structure talks to you, especially a concrete structure. If you have significant, concerning shear and flexural cracks, you probably should be looking at a strengthening project or maybe a bridge replacement. You may be able to get the numbers to pencil out by doing a live load test, right? Those trucks are driving across. They are making it across. But you have to, as an owner, decide what is it that you're really trying to accomplish. And to me, these tests are really geared towards a structure that is in good condition that you're trying to keep. ODOT's been doing more refined analysis as of late. It is a cheap alternative. If you have a good idea of your boundary conditions, using a grillage analysis, go after those live load distribution factors that AASHTO are typically conservative on, right? Engineers, we make our assumptions, and we typically have those be conservative. So typically at ODOT, at least, we like to go the refined analysis route first. If we're comfortable with the boundary conditions, it may not come with a load test. If we're questionable on the boundary conditions, a refined analysis may need to be accompanied by a load test just to validate our models. So when not to load test. So the cost of testing exceeds the cost of strengthening. In my experience, strengthening is typically more expensive than testing, but if you're pretty sure your test is not gonna work or you have one of those structures that are in poor condition, strengthening might just be the better option anyways. Pre-test evaluation shows the load test is unlikely to improve the rating. If you have a possibility of a sudden failure or access and traffic control, this means you're just not gonna get out on that bridge deck. To do a load test, you really need to be able to close the structure to traffic briefly, does not have to be for very long, so that you can have your controlled testing load go over it. And that's both with a diagnostic or a proof test. You need to have that control of what is on that structure, why I'm testing it. What am I measuring? So just kind of some of the basic instrumentation. There is a whole slew of instrumentation. I am not an expert on any of this stuff. Start getting into the millivolts and all the different strain gauges. It's not my area of expertise. This is what ODOT has. It's not the fanciest of systems by any means. There are some suppliers out in this other room that would be happy to help you find some maybe a little bit more modern equipment, but this is what ODOT purchased and is used quite frequently. We do have BDI strain gauges that we use for concrete or steel. Typically weld-on uniaxial strain gauges are our workhorse for measuring strain on steel members. There's displacement transducers, there's rotational gauges. Anything you want to measure, someone has a sensor out there for you that will do the job. I should also mention the intent of this presentation is not to make you an expert at load testing, but it's at least to let you know that this is a tool in your toolbox and one that can be a very valuable tool for both owners and those that are advising the owners how to make decisions on bridges in their inventory. So, Bridge of the Gods, our first case study, proof test. I love when I talk to people about it being a bridge engineer in Oregon, they always assume I work on structures like this. I did work on the structure, just not that part of it. This is the approach span. This is typically more where I actually do work, right? It's the small little overpass. It's stuff you don't even really notice as a bridge when you drive over it, but it counts. There was the Oregon approach span on the structure that actually gave us the challenges. It's a 3-span steel plate girder bridge, has a suspended span in the middle. It is a built-up plate girder that has mechanical fasteners, rivets that connect steel plate angles and cover plates in order to make up an I section. A load rating was done on this. It assumed non-composite action. There is no mechanical fasteners intentionally placed there to make the deck composite with those steel plate girders. It's a big key is that they were not intentionally put there to make that happen. We did hire a GPR company and did a little bit of exploratory testing to try and hope and find some fasteners there. We were unable to find any. So we had to operate under the assumption that that steel girder is not working with the concrete deck. You do that and you end up with a 6-ton posting. Again, this structure is in good shape. It's been in service for a long time and it operates on things well above 6 tons. Controlling load effect on it was Moment at mid-span. Here's just kind of a section of that steel plate girder. You can see the built-up cover plates on it. We assumed that likely the reason why this is performing so much better than our assumptions, our engineering assumptions were, is that that deck probably is actually working with it. There's a lot of connections between the two. The question is what level are those connections going to be relied upon? And there's not a great deal of research on this. Unless they do research in the room, maybe a good area to explore for us. It'd help some of us owners out, but there's been research that says that somewhere between low loads and high loads, that bond will suddenly break and you will lose that composite action and that you will not necessarily have a terrific warning before it happens. So it's hard to rely upon with the current research that's out there. So in this case, doing a diagnostic load test was not really what we were going after. It's a 2-girder system, right? We're pretty sure the truck loads are going into one of those 2 girders, so we're not trying to refine our live load lateral assumptions. We're trying to say, well, is that deck composite and at what levels can we rely upon it? So that was why we landed on a proof test. It can be relied upon at certain levels, right? So we kind of very slowly and incrementally increase the loads and have monitoring on the structure to look for nonlinear behavior. I'll kind of run through that instrumentation. We installed displacement transducers at the quarter point and end point of the spans, the location of those red triangles. This is kind of what it looks like. Basically, just a channel attached to the deck. The sensor is actually attached to the steel member and you have a very sensitive displacement sensor in between the two and you're looking for slip, right? If there's non-composite action, you should see the ends of the span start to come loose first and give you a warning. We also wanted to measure the neutral axis and see what the strains are actually happening, right? If that deck is working with the girder, that neutral axis is not going to be in the middle of that member, it's going to be up high on it. And so we installed uniaxial strain gauges on the mid-span and quarter points. So anyways, we have 3 uniaxial strain gauges, 2 on the web and 1 on the bottom cover plate. If you believe our theory that plane sections remain plane, you should be able to draw a line between all those strain gauge readings and have it be a straight line and then be able to get your neutral axis off that. It's kind of showing it's just above that lower angle for that lower strain gauge location. Here it already has the environmental protection on it, so not a lot to see on the picture. Again, the goal of the proof test was to have, so on this structure, it was posted previously for a very long time of its life by the bridge owner. ODOT does not actually own this structure. It's Port of Cascade Locks for legal loads. And so that's really all they wanted to get back to. Again, that was one of our criteria for doing a proof test. is if you're okay with legal loads, then we got a possible solution for you. A target live load factor is used, and this is following the manual for bridge evaluation, to scale up your proof load to your target test load. So if you have a legal truck you want to run on that bridge unrestricted, you're going to have to scale that truck up so that we now build that factor of, factor safety is the wrong term, but build that buffer between what we've tested and what we allow, right? Handle that variability. Manual bridge evaluation gives you a list of adjustment factors that you can use as part of this. You know, things like if the bridge is in poor condition, you pay a penalty, you make your factor bigger. If you have good inspection on your bridge, well, now you get a little help and you're going back down. And so some of the factors that go into it. It ranges, it starts at 1.4 and then scales up or down based on how these factors apply to it. We ran through it for our target test load and we came up with 1.33 is the factor that we are going to use on this proof test. 1.3 is the minimum and 2.2 is the maximum. So you figure when you're talking about putting more load on the structure than it's seen, I mean, if you have to take your legal truck and multiply it by 2.2, and then set that on the bridge, you're probably stacking barrier on it to actually achieve loads that high, because I don't think you could actually drive something on the structure that would quite do that. This is just a calculation. Impact was not included as part of this test, right? These are quasi-static tests. You're rolling out onto the bridge very slowly. We know operating conditions. You actually have a truck that drives across it, so you have to increase for impact loading. And so you have that LR is that target loading or that load rating one that you're trying to get to. I need to get at least this truck on the bridge when I'm done. You magnify it by that X sub PA factor, which was that scale factor for our conservatism, and then you also multiply it by impact because that's not included in our test. And then you end up taking something that was like 1,000 kip feet and you magnify it almost up to 1,500. We got a couple 10-yard dump trucks, and these are our ODOT maintenance forces helped us out with this. They're never super enthusiastic when you tell them you want to do a proof test with them. So we typically have, like, I'm on the deck lining them up, right? That shows a little range of confidence. Just by habit, a lot of times instrumentation is installed underneath the bridge, so you got another guy down there. So we're kind of trying to show some confidence. But anyways, we got in there. We ran through 9 different loading scenarios, put some paint down on the deck to help guide them and line them up where you want them. Right, again, this is a controlled test. You want to know where they're at. So we got to our final loading. We did 2 fully loaded dump trucks parked back to back. We get those axles centered over the mid-span there. Get the 2 sets of tandems in that very short distance. The guy on the right here, he was really ambitious. So you could see his tires squishing out just a little bit. He said, "How much weight do you want me to put in my truck?" I said, "More is better." Fortunately, he didn't have to cross any bridges on his way to our proof test bridge, so we were okay with that. Just kind of an example of showing the loads on there and the moment diagram that we actually induced in the structure. And just kind of looking at that 4 axles in the mid-span there, you can see that one guy was up in the 18 kips per axle range and the other one 16 kips. Total gross vehicle weight was 121,000 pounds, which is 2 sets of tandems, which was 86,000 pounds over just 15 feet. So again, getting at that, we're putting some load into it, right? We're proving that that bridge can hold the weight. It produced a mid-span test moment of 1,400 kip feet. We had no slippage or inelastic deformation through any of the tests, right? And so we worked our way up to this slowly, right? We knew we were putting a lot of weight on it, 9 load cases. So you start out with like an empty truck, which is almost kind of comical because clearly that's already driving across the bridge now anyway. So that wasn't really a proof, but it was just kind of to monitor the trends over as it kind of went through the testing. We measured a neutral axis from our strain gauges. It was in pretty close agreement with our theoretical. There's a lot of things you could explain the difference. I would just say most likely it's the fact that, theoretical, we take that whole deck top flange or concrete deck and make that our top flange. We have a lot of shear lag and other things that are going into that, but pretty close. And certainly nowhere near non-composite, right? Non-composite would have been at mid-height of it, which was 25 inches versus what we measured, which was 43. So we were definitely showing that there was composite action there. It was repeatable through all of our load tests, or all of our test scenarios, I should say. Kind of a graphical representation of those strain gauges with the actual, so this is the maximum load test that we did. You can see you draw a nice little straight line through there, measure your neutral axis. All 3 strains line up with each other. So you got to establish an operating capacity based on that, and that's basically just backing back out from your proof test to your factors. The one factor I would mention here was the one I have not had to use, but it's K naught. This is your you didn't reach your test load factor. So if for some reason during your test you start seeing some inelastic deformation, you found the limit, right? It is time to stop. And so now you're backing down further from that. You didn't reach your target test load. In our case, we've reached it, and so we got a 1.0 on that. Just again, some of the numbers that go into here. This is all covered in the manual for bridge evaluation. For the sake of time, we'll just kind of gloss through it a little bit here. But one of the things I would like to kind of highlight is just go back into the rating factors. You can see for Oregon, we have a lot of vehicles that we rate for. But if you look over here, you have your legal trucks. These are your 3 legals. We got those. This guy just barely eked by 1.00, right? We had that target. You start getting in your short haul vehicles. These 7-axle guys are still restricted today. And then you get into your permit loads and we couldn't get them. So if I was really trying to get this 5BW permit to pass, I would have had to really doubled up that load more or less on that structure in order to get it to happen. And so it's not, that's why we're saying it, to me, it doesn't make a lot of sense to try and go quite that far with the proof test. So we did, again, verify composite action. We updated the rating factors per Chapter 8 of the bridge manual for bridge evaluation. We took away the 6-ton posting limit and put on the new one, which was back to legal trucks. The owner was happy. Here's the next bridge I have here. This is the Powder River Bridge Street, and this is a diagnostic test. These are the ones where you get that bang for your buck. You can really kind of turn things around on it. You can sharpen the pencil, but really sharpen your understanding of how the structure behaves. So these are single span rolled steel girders with a composite reinforced concrete deck. These ones was not subject to question. They actually had studs welded onto the girder, so I knew the deck worked with them. It's a 27-foot bridge, 56 feet wide, originally constructed in 33 and widened in 60. I see this all the time on Oregon's bridges. I don't know if everyone else has the same problem, but they widened our bridges in the 60s or so, assuming that they would be probably replaced somewhere down the line. And here we are, we're still with them. The bridge is actually not in bad condition, so that's fine. We'll keep it in inventory, but at some point we might have to start replacing some of these things. 28 girder lines, 2-foot spacing, very tight girder spacing, right? Not too worried about the deck failing on this one. You're not going to punch anything through there. The widening project caused 2 longitudinal joints in the deck. Actually at unusual spots, but I'll show them here in a minute. But these longitudinal joints were a key problem in our load rating. Performed that load rating and found that mid-span flexure of the original steel girders controlled. It actually wasn't a severe load posting. This one was going to be, legal trucks were going to be okay on it. It was all the permit trucks that were going to be a problem with some level of restriction. When we reached out to the owners in the area, they came back to us with, no, this is a huge problem for us. We can't handle this restriction. We need something else to happen. So you kind of started looking at it a little closer. So just a view from it up above. If you weren't a bridge person, you probably wouldn't notice that you're driving across a bridge. From underneath, there's our whole stack of fairly small steel I-beams, but lots of them. Those longitudinal joints that were built into the deck, not the best diaphragm bracing there, but it's there to some fashion. Okay, so here's the plan view of the bridge. Here's the original structure, and they widened it on both sides. And then as part of the construction staging, they added 2 longitudinal joints, one into the original structure. Right? I saw an unusual look from the audience there, right? I'm not sure why they did that either. It did not make sense. It's a very wide structure to start with, but they like to give us challenges and let the future generations figure it out. We did that LRFR analysis, and how much distribution you get across a longitudinal joint? 0, or some. But on paper, you're gonna have to say 0, because how are you gonna quantify that distribution? And so when you do that and you have a joint running down the middle of your structure, you can set a wheel line right on that, and it's basically like an exterior girder, but it's right in the middle of your bridge. It does not rate out well, right? You got anytime you see lever rule and you have more than 2 girder lines on a bridge, there is a very good chance that live load testing could help you out a lot, or refined analysis for that matter. So this one, lever rule with an interior girder, although it was exterior-ish. Due to the tight spacing and those longitudinal joints, we figured that there's probably a lot better load sharing that's going on that we were having a hard time quantifying, and that was why we moved forward with the load test. So what did I say? There was like 28 girder lines on this. We were not going to instrument all of them. I don't have equipment for that. We did girders 15, 16, 17, 18, and then hopped over to one of the newer girders there. So we've kind of bracketed those 2 longitudinal joints that were giving us the trouble. We did our diagnostic test, right? We're really going after what's that lateral load sharing. We just welded strain gauges to the bottom. The end conditions of these bridges are just simply supported on the girder, so we didn't think we had a lot of unknowns throughout the structure. It was really where's the lateral load going? We did 4 different static load configurations to make sure we kind of found that key loading, the worst case loading. And then we updated the load rating per section 8.8.2 of the bridge MBE. Just kind of an example of that weld-on strain gauge there at the bottom flange of the girder. Used a 80,000 pound, again, 10-yard dump truck. This is kind of our bread and butter here. It's representative of the type 3 load case. I'll get into this magnitude of load piece, but you pay a penalty when you do this type of a load test if you don't have a load that's high enough to represent a lot of the vehicles that you're trying to encompass. Put a lot of paint lines down on the bridge and have the drivers kind of roll across it, have to hold traffic while you do it. Again, this is like a quasi-static, so it's just a slow roll across the bridge. We're not trying to include the dynamic effects. When we went through and compared our strains, we noticed that, boy, there is a lot of load sharing on this structure. And so I'll kind of highlight here the ones on the top. You have girders 17 and 18 here, and then these ones here. You hop to the next slide, and there's a longitudinal joint here and one here. And so theoretically, this truck is only being carried by these 4 girder lines. And no load should be transmitting across to girders 22, 16, or 15. But when you look at the graph, they're carrying a lot of load. Right? So that's where we're getting a much better performance. That's where paper is not meeting reality. Updating a load test, if you follow the manual for bridge evaluation on this section, is really quick. There's this K factor. You just go right to your rating factors of your load rating and multiply it by that, and you get the bang for your buck. I would not say that this is the only way to update a load rating, but it's the one that the MBE calls out for. You have a KA and a KB factor here. KB is where you pay the penalty for not having a heavy enough vehicle if you compare the load effects. So run through and kind of compare that measured strain versus the theoretical strain. You can see there's 3, 4, 5 times difference of what we would have expected the strain to be versus what we measured. No, sorry, I've said that the backwards way. Flip that around and you got it. The strain measured is a lot lower than what you would actually do in theory. Update the rating factors, and all of a sudden we went from a bridge that was restricted to one that has all kinds of load capacity. The district was very happy, and we were happy to not have to replace the structure, which is what they were pushing for until this happened. Or strengthening 28 girder lines, also not something you were really trying to do. And that was really what it was. This lateral distribution was much higher than what we would have done in theory. The longitudinal joints, and the asphalt showed this, there was no cracking or distress in the asphalt above those longitudinal joints. They've been there for a very long time. They just kind of bridged the loads. We removed all the permits. So is load testing preservation, right? So it depends on who you ask. So if you're asking for FHWA preservation funds, the answer is no. But I like to look at preservation in a bigger sense. Like preservation is keeping good bridges in my inventory, right? We got to replace the ones that we can't preserve anymore. And the only way you can do that is if you stop replacing the ones that you could. Preserving a structure doesn't benefit the public if we turn around and knock it down. I've had bridges where we've done deck seals and then turned around and took them out not very long after. I did not get very good use out of my deck seal on that bridge. In fact, I could have done nothing to that bridge for its entire life. We did end up replacing it after a short period of time. There are multiple companies at this conference that could help with this. I would suggest seeking them out there. If it's not something you've done as an owner, like I said, we'll have a peer exchange in the following session. There's my contact information. I don't even think I gave you an option for questions. But anyways, thanks.
The preceding was produced by the National Center for Pavement Preservation. More information can be found on the web at pavementpreservation.org. Additional support provided by Michigan State University.